All right. Looks like we are live. Hello and welcome to Mr. Linford's math course. Today, for our live stream, I figured we would go over the group project that people had to submit the other week. The first group project, which was about common ancestors. I like to go over the entire project and highlight some areas that students might have messed up on and some areas where I wanted to point out some of the mathematics that were at play. If you have any questions, please let me know. We have a live chat going on to the side. And hopefully, maybe once we're done with this, if you have any questions about the new group project, I might be able to talk about that as well. So let's first go ahead and let me queue up the original project. So let's try to get this set. So what you had to do was read through this project and then answer the given questions and run through a specific simulation. Now, the first part really talks about the idea of a common ancestor. And if you think about it, how many people we have what's called a blood relation to, how many people we are directly related to, whether that be a sibling, a parent, a step-sibling, a grandparent, an aunt, an uncle, a cousin, people that you're related to by blood, not by marriage and not by adoption, but people you are actually share some type of DNA with. Now, as you branch out further and further, right, our connections to people, they don't always, they're not always the strongest, right? Like as you branch out to your second and third cousins or maybe your great uncles and great aunts. Maybe these are people you have never seen or people you haven't seen for years, and maybe you only share a little bit of DNA makeup with them, right? But we still say there's a blood relation. We still consider them some type of a relative. And if you think about it, there are a lot of people in this world that you are related to by blood, right? If you think about your parents and your siblings, your grandparents, okay, that makes sense. But then start branching out. Your aunts, your uncles that you're related to. Start thinking about your cousins. What about your great aunts and your great uncles and your great grandparents and your second and third cousins, right? As you start moving out more horizontally on your family tree, there are a lot of people that you could be connected to, especially if you come from a large family. Now, if you think about it, there are a lot of people that we're all connected to. Doesn't it make sense that maybe at a certain point, several of us could be, in fact, related to each other to some degree? This kind of came about, this problem came about with the discussion of royal families. I don't know if you've ever heard the phrase, but if you're from Europe, people will tend to claim that they are a direct descendant. If they're of European descent or European origins, they tend to claim that they are a direct descent of Charlemagne. Charlemagne was the emperor of the first emperor of the Holy Roman Empire, and big figurehead in Europe. The Holy Roman Empire, really, I think it was in the Germanic area, I want to say, of Europe. But a lot of times people claim direct lineage from Charlemagne, the emperor. And, they tend to bring it up at family get-togethers, or they tend to share, with simple stories. Because it's fun to claim, that you're related to famous people, right? But the trouble is it turns out, most likely, probably everyone of European descent is related to Charlemagne. The idea is if you go back far enough in time, you will find an ancestor that's related to everybody in the present day. So this is how the simulation was supposed to work. I'm going to pull up a picture here of my simulation. We started with 6 people in the present day, and I picked the number 4 to represent myself. And what I did was I rolled a die several times for each person. I started with person number 1 and I rolled the die. And I saw which numbers popped up. Now this row right here, this second row, represents the parent generation. This is the current generation we're in, and this represents our parents' generation. So I'm going through these 6 people, and I'm going to decide who their parents were. So I rolled a die to decide, and person 1 had the parent 3 and the parent 4. Person 2 had the parent 3 and the parent 6. Person 3 had the parent 2 and the parent 4. Person 4's parents were 1 and 2. Person's 5 parents were 3 and 1. And person 6 had the parents 4 and 2. Now you'll notice of this generation, the parents' generation, person 5 never had children. So what I did was I labeled a little n next to them, meaning they're related to no one in the present day. They didn't have children, their lineage stopped, they're not related to anyone currently. However, all of these other people are related to someone in the present generation, some more than others. So what I did was I wrote the numbers of the people that were in the present generation, who they're related to. So person 6 here, they're related to person 2 in the present generation. Person 4 here, they're related to persons 1 and 3 and 6. Person 3 is related to 1, 2, and 5. Person 2 is related to 3, 4, and 6. And person 1 is related to 4 and 5. That's who they're related to in the present generation. What you then had to do was repeat this process, this time for the grandparent generation. That's this row 3 right here. They represent the grandparent generation. So I'm going to figure out for these parents who their parents were. So I rolled the die again. Person 1 here was related to 3 and 6. Okay? Person 2 here was related to, it looks like person 6 as well. I rolled the die twice, and I got the 6 both times. For our simulation, it really doesn't matter. That doesn't really make sense biologically. One person can't have a child by themselves. They can't just, clone themselves and reproduce by themselves individually. But for our simulation, it didn't really matter. I could have rolled the die again or just left it, so I just left it as is. Person 3 had the parents 4 and 2. Person 4 had the parents 1 and 4. Person 5 had parents 1 and it looks like 3. And person 6 had the parent 3 and parent 5. Again, you'll notice person 6 here. Oops, I think I just skipped a generation. Right, whatever. I just did the grandparent to great-grandparent generation. My bad. Hopefully you get the idea, right? We're just seeing the current generation's connected to the parents, and the parents are connected to the grandparents, and then the grandparents are connected to the great-grandparents, and they're connected to the great-great-grandparents. Okay, hopefully you're getting that idea. Now, oops, let me see here. Okay. As we're working through this, I continue to always write who people are related to in the present generation. So that made sense for the parent row, right? I labeled who their children were. For the grandparent row, we need to label who their grandchildren are. For example, let's take a look at person number 6 here. So this is grandparent number 6. They had the child number 6, and they had child number 1. So this person right here and this person right here were the children of this person, person 6. Now, a lot of students in their simulation labeled, oh, this person is related to 1 and child 6. That's not what we were supposed to do. We're supposed to label who they're related to in the present generation. These numbers represent who these people's children were. These numbers represent who these people's grandchildren were. So notice right here, this person was related to 4 and 5 in the present generation. So this person 6 here is also related to 4 and 5. This person's related to 2 in the present generation, so this person's also related to person 2 in the present generation. Okay? All that we did here was we labeled who their grandchildren are. Okay? And then as we work backwards more to the great-grandparents, we labeled who their great-grandchildren are. Now, if you come across this person right here, this is the first person who's related to everyone in the present day. Okay? They had a child who had kids 4 and 5. They had a child here who had kids 1, 2, and 5. they had a child here who had kids 1, 3, and 6, and this kid had child number 2. So, who is this person related to in the present day? Well, they're related to person 1, person 2, person 3, person 4, 5, and 6. They're related to everyone in the present day because their children basically had all of the children in the present generation. Okay? That's why this person is what's called our most recent common ancestor, the person we're all related to, the first person we are all related to. As you work backwards, you start to find that the common ancestors start popping up more and more. It appears that more people are related to everyone in the present day. And then you finally go back to this generation right here. Again, you might have had this happen a generation earlier or a couple generations later, but because we're rolling random die here. But for me, this, let's see, that's the present, parent, grandparent, great-grandparent. This is the great-great-grandparent generation. Here, every person is related to everyone in the present day, or they're related to no one, because that's a possibility too, that they just had no children. Otherwise, if they did have children, they're related to everyone. So this is what's called the identical ancestor generation. This is the generation where literally everyone living at this time has descendants in the current generation, or they're related to no one. Okay, so we could say that again, this is just a simulation of 6 people, but we would be able to say we're related to all of these people at this point in time. Okay? Or we're related to none of them. But that's the idea that's trying to come about here. This came about from a study done by a Yale statistician, and what he was trying to do is really take this simulation, apply some information to it, such as migration patterns, geographic information, but really he used this type of setup with current populations to try to determine when certain things like a common ancestor or an identical ancestor generation might occur. Now, I think in the paper originally, he was focusing on Europe because Europe has a lot of data and information about in historical records about people and the census, etc., mostly where the Roman Empire existed. But he also, in the paper, talks about I believe Asia and Africa. I think he has some models that also work for Asia as well. Now let's get back to this practice. That was how the simulation was supposed to run. Now, you were then asked a series of math questions based on the formulas that we have from this Yale study. So in this study, Joseph Chang suggests that if you want to find the number of generations since the most recent common ancestor, right? How many rows back would it be, right? How many generations back? You use this formula. 2 to the Tn equals n. N here is the population of the present generation. See, I say that right here. Let the number of people in the present day population you're examining be represented by n. That's how many people are in the present population. In our example, that was 6. And if you find t to n, this power here, that's the number of generations back till we find that someone's related to everyone. If you want to find the identical ancestor generation, that's the generation where everyone in the generation is related to everyone in the present, or they're related to no one. That's the U of n formula. That's this one right here. Again, n is the population of the present, and un is how many generations back until we get to that. So let me show you on my picture here. This person E, is about 3 generations back. So they represent the common ancestor, the most recent common ancestor. This generation at the top row is the identical ancestor generation, and they're about 1, 2, 3, 4, 5 generations back, let's say. So that's the idea of what's going on here. These are the 2 formulas that we have to work with. So In problem number 1, we need to use the formulas to estimate how many generations it's been since the most recent common ancestor. Don't use your drawing here. All right, we're using the formulas to test this. So let me pull my iPad up here. Oops. Let me move it a little bit. So how many generations since the most recent common ancestor? That means we're working with the Tn formula. 2 to the Tn power equals n. Now we're saying for our simulation, how many people were in the present population? 6. So we are trying to solve 2 to the Tn power equals 6. Take a minute. What are we trying to find here? Hopefully you realize that essentially we're trying to find an exponent. And in finding a missing exponent, we will figure out what Tn is. But how do we go about finding a missing exponent? I had a lot of students asking me, wait a minute, 2 to some power, that doesn't get us 6. 2 to the first power is 2, right? 2 to the second power is 4. 2 to the third power is 8. Where does 6 come from? Well, it's not going to be a whole number, right? That's why I say round your answer to the nearest integer. Really, think about this for a minute. 2 to some power is 6. How do we figure out a missing exponent? That's a logarithmic problem. That's the most straightforward logarithmic problem that you could have. So to find Tn, you need to take log base 2 of 6. Okay? That's it. And if you remember, you could type this into your calculator if you have a graphing calculator that lets you change the base. But otherwise, we could use the change of base formula. We could do log base 10 of 6 divided by log base 10 of 2. And if you did that, I'm typing in my calculator right now, you get about, Tn is about 2.58. Roughly, if we round to the nearest whole number, it's roughly 3 generations back, okay? This is how you solve the problem. This is a logarithmic problem, as basic as it can be, okay? Let's take a look at the next problem. Use the formula to estimate the number of generations since the identical ancestor generation of your simulation. All right, here's the formula. 2 to the un equals n to the 1.768 power. This is for our simulation, so n here is 6. All right, well, I can figure out what 6 to the 1.768 power is. I'll just put that in my calculator. Some long decimal, but whatever. And in fact, you know what? Let's use some properties of logarithms. Why not? I can rewrite this as u to the n equals log base 2 of 6 to the 1.768 power. And exponents can be brought out front in logarithms, so u to the n equals 1.768 log 2 of 6. So let's use our change of base formula, log 2 divided by log 6. Log 6 divided by log 2, just like we did in the previous problem, but now we need to multiply it by 1.768. You should get about, that's 4.57. So that rounds to about 5. This was all you had to do for the math. I had a lot of students emailing me, well, not a lot, but I had several students emailing me. They've never done problems like this. They've, never seen anything like this common ancestor thing. How are we supposed to go? That wasn't really the point of it, right? This is just a theme to a problem. I could have come up with any other theme, any other application to logarithms. Essentially, this is just a logarithmic problem. 2 to some power gets you a number. So one of the things that we need to be able to do is say to ourselves, to kind of calm our thinking and say, wait a minute. if we are going to essentially try to find a missing exponent here, how do we do that? Now, in the previous week, we had worked through a few days of logarithmic problems, and then in the week after that, we actually did problem-solving logarithmic equations. So you should have known what a logarithm was and how it was supposed to be solved. In the next problem, I gave you the population of Europe. And I said, let's repeat this process, but now let's work with actual numbers. So let's work with the current population of Europe. The current population of Europe is about 741 million people. Okay? Let's figure out their most recent common ancestor. That's the TN formula. 2 to the TN equals N. N is the population. So that's 741 million. And that's equal to 2 to the TN power. How do we find a missing exponent? From now on, you have to say logarithm. To find that missing exponent, you need to take the logarithm. The base is 2. The argument is 741 million. This is a very simple problem to be done. Just use your calculator. Graphing calculator, scientific calculator. You can even Google how to do this on Google's calculator. And I get about 29.46. So that's about 29 generations back. Another issue I saw a lot, students not knowing how to round. 29.4, right? People would round that up to 30. No, don't do that, right? Some people said, well, 29.46, round the 6 up, right? So you get 29.5. When you're at 29.5, you round that up to 30. We don't do repetitive rounding, right? Then you can round to whatever you can force it to round to whatever you want, way higher, in fact. You don't do that, right? We don't keep performing rounding several steps at a time. If you're going to round to the nearest whole number, you look at the previous number. You look at the previous digit, okay? If that is less than 5, round down. If it's 5 or above, round up. Didn't think I needed to go over rounding in Algebra 2. But please make sure you're careful about that. Those are like little things where people can get points taken off that I want to make sure that we understand. Let's do the last situation here. We're using these formulas. We want to find the identical ancestor generation. So that was the UN problem. 2 to the UN equals n to the 1.768 power. I think that's what it was, actually. Hold on a second. Let me just 1.768. Cool. So here we go. Let's try to do this for 741 million people. If you're given a formula, you got to say to yourself, do I know any of the information of the formula? Yeah, I kept telling you the population. So 2 to this UN power is 741 million. And that's to the 1.768 power. Now with this, we can change this into a logarithm. UN, that generation number I want to know, is the log of base 2 with the argument 741 million, and the exponent on that is 1.768. Now, when you're working with logarithms, you could move the exponent out front. You could leave it, right? You could actually figure out what this is in your calculator. But let's go ahead and maybe make it a little easier for ourselves. 1.768 times log base 2 of 741 million. I'm going to grab my calculator here. Let's do log 741 million. I'm going to divide that by log 2 so I can do the change of base formula. And then I'm going to multiply that by 1.768. That is about 52.09 generations back. So that's about 52 generations. And that's it. That was essentially all that you had to do for these 4 problems. They were the same type of logarithm problem, just again and again with different numbers for n. Now, number 5 here says, okay, we're talking about generations, but like how many years ago is that? Typically, in sociology terms, a generation is about 30 years. So if I said something like we're 52 generations back, I mean 52 times 30. So let me move this up here. So this is the number of generations. That's how many rows back in the simulation I'm at, right? So what does this mean in terms of years? Well, 52 generations times 30 years per generation gets me 1,560 years. I'm that far into the past. Let's see, the year is 2020, and if it's that many years ago, UN, this identical ancestor generation, that occurs in the year 460 AD. That is how far back we would have to go to find a generation, again, estimated, where everyone in that at that point in time is related to everyone in the present day. Okay? Everyone at that point in time, if they have children, they're related to everyone in the present day, or maybe they're related to no one in the present. Okay? Now, this was essentially the only math that you had to do for this. A big thing that students tended to trip up on was that they lost sight of the problem. They got wrapped up too much into all of the situation. You have to be weary of that. You have to be careful of that. You can't get wrapped up in what's the theme of the problem, right? Like if I write a simple problem like an office problem or a Batman superhero whatever problem, don't get lost in what the theme is, okay? What I want you to do is really just say, okay, here's a formula. I'm asked to solve for this unknown. And do what other information? Oh, I'm given the population. Oh, I'm told that's what n is. That's the thinking that you need to start being able to do here. You need to say, okay, well, if I'm working with this formula, here's what I'm trying to solve for. What information am I given? That's the Polya method we learned about in class if you're in my algebra courses. But this is the type of thinking that we need to have, especially with word problems. So take them a little slower and don't get too wrapped up in like the theme of what's going on. If you read through the reflection questions, a lot of people put some good thought into these. What are some problems with our simulation? Well, everyone pretty much said, okay, well, there's only 6 people. That's not really a problem with our simulation. I mean, yeah, it doesn't really, there's not only 6 people in a generation or a population, really. But what you should be considering is, well, this is a simulation. So in what ways is it not accurate? Yeah, you could say by being the very nature of being a simulation, it's not accurate. But I was looking for more other descriptive things. So some people said, well, for example, there's always 6 people in each generation. Right? It's not like it's a growing population where it expands outward, or it's a decreasing population, right? There's always 6 people. What if there was a pandemic, let's say, and people died off? What if, people had more than 2, 3? What if someone had more than 6 kids? Then right away you have a population of over 7 people, or 7 or more. And then they started pointing out, there was this idea of it being totally random who the parents were, right? I think it's, pretty... the thought of like, okay, you could be related to anybody. Well, that's not necessarily true. Based on your geography, you're not going to, have a parent necessarily from, if you're born here in America, you're not going to have a parent, if you're born in Michigan, let's even say, it's not as likely that your parents are going to be from a very specific area out west. Most likely your parents are going to have been from Michigan or have been living in the Michigan area, right? There's more of a likelihood that your parents are from the area that you're born in. Then other people pointed out that, yeah, there were multiple different partners having children, right? So person one and person two had the same children, and then person one and person three. So it's like, and we didn't take gender into consideration or biological sex into consideration. So it was, there were some, obvious pairings up that, couldn't necessarily happen to produce an offspring. So there were some faults, obviously, in some of our assumptions to the simulation where it probably wouldn't have matched up how a genealogy worked, right? So this was kind of a rough formulation of it. However, when people were asked, were Chang's formulas, the mathematician or the statistician from Yale, were the formulas pretty accurate? Actually, yeah, they were pretty accurate for our simulations, right? I know they were for me. They were, I think 3 and 5 were the numbers I got, which were, 5 for the identical generation and 3 for the common ancestor. And that's actually the rows that it occurred in. That's how many generations back it was. So for me, it was very accurate. And I think a lot of people found that the formulas were pretty accurate for their situations as well. Or it might have been off by 1. Now, how did the size of the population affect how long ago the most recent common ancestor occurred? Obviously, if you have more people, the most recent common ancestor is going to occur much later than if you only have 6 people. So when it came to the most recent common ancestor for Europe, you notice it was 29 generations back? I think it was, about 29 generations back, as opposed to just 3 generations. And why was this? A lot of people said, well, because there's more people. Well, that's not very descriptive, is it? When you're asked to explain why do you think this is, think about it more like this. Yes, as there's more people, there are more possibility of different connections. Okay? So to get everyone, to be related to everyone, you have to be connected to all of those connections. It's going to take more time to establish those connections. And in a random simulation like this, where we're just rolling a die, a lot of people don't realize that it's not always an even distribution over every time, right? Sometimes you have clusters. We saw some clusters in our examples where someone had a lot of children for a generation and someone had no children, let's say. So you might find that someone might have been related to a lot of people. There might have been clusters where this person was assigned to several children, right? And that's a possibility. Again, you're just rolling a random die here. You're basically randomly assigning people to parents. Should we use Chang's formulas to model the common ancestors of Asia and Africa? Because Chang used these formulas to model Europe, should we use the same for Asia and Africa? Now, some people said, well, no, because they're different continents, they're different geographies, they're different, they have different geographic patterns, and migration patterns that you would have to take into consideration before just applying what happened in Europe. Other people pointed out, look at our simulation. You're just randomly assigning someone to 2 parents. So, yeah, you could use Chang's formulas. So for this answer, it's a little bit yes and a little bit no. The common ancestor formula, you could definitely apply. Because, again, it's just randomly assigning some people to 2 parents and then looking to see when this might happen. Now, if you wanted to get more technical, especially with the identical ancestor generation, you want to be a little more careful. Part of that is built off of looking at really simulations, but Chang has also in the paper cited, looking at migration patterns, looking at geographic information, and when you go into a different continent, you'd have to establish the migration patterns of that continent and look at that information as well as historical information. The trouble is where the Roman Empire conquered, there's enormous bookkeeping records. So when the Roman Empire expanded throughout Europe, those areas, there's a lot of documentation. That's one of the great things about that the Roman Empire did was they recorded everything. They wrote things down. So we have quite a lot of information about society back then. In fact, census information, weather patterns, crop information, economic information. So we can kind of see the migration of people over time. And we can kind of get a pretty good picture of the way society was and how many people were around back then. Africa, not so much. There wasn't really bookkeeping or records keeping so much, especially not throughout the majority of the continent. Maybe in North Africa more so. So it's harder to identify, okay, how many people were in a specific area at a specific time. More so you have to look to see, again, where might people have migrated? Where would it have been most likely that they would have migrated? What was going on at the time? And without solid records, it's hard to identify all of that. Same with Asia. Asia, again, is such a widespread, these are large continents, right, that they're taking into consideration. So you might know a small area of the continent, but to establish that for the entire area, it's pretty difficult. So could you do a simulation like we did for Europe with these two other continents? Sure. However, when it gets to knowing more details about it, like the identical ancestor generation, that's when it gets a little more difficult. So I gave people points either way if they said yes or no, and as long as they justified their answer, we were good. And that was pretty much it for this project, okay? I hope it makes sense. I wanted to run through the simulation first and show people where they might have made their mistakes, and then I really wanted to run through and show people how to really apply the math of it that we were learning to solve these situations. Really, it comes down to being very careful in your reading, and I always say calming your mind. Don't be too nervous about a problem and get roped up into all these little details. What am I being asked to solve for? I need to find Tn. Here's a formula for it. Well, how can I find that? What information do I know? Well, I'm told what n the population is. So then ask yourself, how do I find a missing exponent? And hopefully it should pop up to you. The idea of a logarithm. So I don't really see any questions here. So I'm just going to end this live stream. Let me know if you do have any questions or if you'd like me to go over anything from the current project that you're working on. Until next time, take care.